Okay, good morning. It's a great pleasure to announce the talk, the first invited talk of the conference by Tran Cao Son, who is a professor at New Mexico State University and has an extensive body of work that spans autonomous agents, knowledge representation, including logic programming and argumentation theory and non-monotonic reasoning, and reasoning about action and change. And this talk is going to bring together the numerous strands of work that Professor Song was working on.
Thank you for the nice introduction, Natasha. And I would like to thank the organizer for the invitations to give the talk. It is a great honor to be here. And as the title said, that I'm going to talk about knowledge representation and automated reasoning. It's kind of, when I get the invitation, I don't really know what I'm going to talk about. So, and it's a joint session, so I wanted to bring the two community together, and that's why I choose this title. And hopefully I convince you that the two community have a lot of things in common, but they also compensate each other quite well. And so that since the area of the AI, like everybody talk about AI these days, I was thinking that maybe I revisit the idea of like what is human level AI program from John McCarthy first, and then fast forward to the current very buzzword is agentic AI in the introduction, and see what we can do, what we can and then going on to the discussion on formalizing action and change in single agent domain, and then multi-agent domain, and then talk about a little bit about the recent exciting work on model reconciliation, and conclude with something on the something that maybe hopefully stir up some discussion afterward at the end. Now, I believe that everything starts with John McCarthy, like in his I cannot either. And the pointer is probably too small to see, but in his 1959 papers, he discussed about the programming with common sense. What does a program need to do or need to have to exhibit the human level common sense, right? So where he mentioned three things. Oh, no. He mentioned, so this is what he wrote about the advice taker. I just copy it from the paper. So there are three things that I wanted to point out here. Is that the first thing is that the program should have, like, whose behavior, the program's behavior should be improvable merely by making statement to it, like telling it about its symbolic environment and what it wants from it, right? And the second thing is to make this statement, you don't really need to have deep knowledge about the program itself. I stay here. I think it may be better. That's it. And then like you don't need to know about the program behavior. You don't need to know about it, but you need to be able to express it, and you don't even need to know what it has been told about, right? So that's also the second thing. The third thing is that like the program should have like machinery to be able to deduce, to be able to reason. Right? So this is the kind of thing that he was talking about, and he also like discussed several features that such a program should address. And but in this paper, he focusing on the one thing, like yes, in order for a program to be able to learn something interesting, or to make something interesting, it must first, I stay. So it must first to be able to talk about it. So we must be able to tell it about it. So that's kind of the emphasis on knowledge representation in reasoning, right? And then he went on to demonstrate how things could work for this simple program from going from the home to the airport by providing a set of axioms and kind of like intuitively give how the agent should create a plan to go from one place. So in essence, in that paper, he kind of laid a kind of research direction for the three things: knowledge representation, reasoning, and reasoning about action and chain and planning, right? So now fast forward to 65 years later, 66 years later now. Here you can see that this is a quote-unquote agentic AI architecture that I copied from a course from Berkeley. And why I'm talking about agentic AI? It is something like astoundingly, a lot of people mention that agentic AI is the future of AI. Now, whether you agree or not, or I agree or not, that's a different story, right? But even like Fai Li, the famous scientist right now in Stanford, was talking about this thing. And this is even more astounding, surprising to me, is that in the first agentic AI summit organized in August this year, you can see that there are 2,000 people in person attendees, and more than 30,000 people attended online. So this is something that I believe that we should not ignore. Right? And if we look carefully at this architecture, what do we see? We see the main component is also action, reasoning, planning, and feedback, and environment, and tools, and all these kind of things. I mean, and then there is also some, in parallel to that, there are some discussion on whether this kind of agent need a word model for like simulation, reasoning, and planning, right? And what is new in there is that if we just omit this part, I believe that a lot of you would agree with me that this is just nothing different than the architecture that we have been discussed about maybe 30 years about autonomous agents. There's not much different, right? So what it is interesting here is that so clearly the LLM or large language model will play an important role in here. I will later, like at the end of the talk, I'll give an example and show you that maybe we can use LLM in certain way that help us, and probably, but that. So let us now move on with a little bit a discussion on reasoning about action and chain and then planning in the past. Like this part, I'm going to talk about like the development up to 2005, and then later on. So now, what is the goal of reasoning about action and change? So the goal is to, from my perception, it is to develop logical representation of dynamic domains that allows for various types of reasoning tasks. For example, hypothetical reasoning, planning, diagnosis, right? And so to represent a domain like the block word domain that we all know about, so what do we need to have? Like we know what we represented it, deciding what are the fluent, what are the action, and what are the effect of the action, and so on and so forth. In general, an action theory is just simply built on a signature of action and fluent, and then the specification of effect of action action executability condition and the constraint among the fluence, right? And depending on the framework that you are using, they may be looking differently, but they would share something. They would address the three main problems in reasoning about action and change, which is like the frame problem, the qualification problem, and the ramification problem. I believe that I don't need to kind of like repeat what are these problems, but it is just like worth mentioning that it took research more than 30 years to completely being able to solve this problem for deterministic action theory, and under a certain assumption that the actions are like we don't care about the time, how much the time, like the effects are instantaneous, and so on and so forth. And to that, what we can see is that we can see like many formalisms that kind of address this problem satisfactorily. Like there is action language, and the syntax may vary, but the thing is we will have like the main thing is like the semantic of each of these formalisms describe a transition function that allow us to predict what is going to be true, to be false after an action is executed, right? So, on the other hand, automated planning, though it so focusing on like developing planning systems that can basically change the state of the world from the initial state, like the initial state here, to a state that satisfies a desirable goal. And the specification of the planning problem or the planning instance, it's basically almost the same as an action theory, with the exception of adding the goal, right? So we have like everything. We need to specify what are the action, what are the effect of the action, and then what is the initial state and what are the goal. So the key concern of like here an example of like, okay, how to go from here to this is a plan, right? And the key concern of planning is like developing methodology to allow to have systems that are efficient, that are scalable, right? So that I believe this is always the goal of planning, developing planning system. But and it's interesting to see that in the automated planning committee also develop like representation language for representing planning problems, and most famously is PDDL and the strips, right? So and today there are so many planning algorithms and approaches that have been developed to solve different kind of planning problem. And I will have this thing here up here. I will make a summarize of all of this in this picture. Please note that this is more or less like it's the time is relative. It's not really the time, but it's relative to different kind of like action representation and different approaches to planning. So you can see that whatever the research in this area or in this area, they share one thing, as I have mentioned earlier, that the idea is that we will need to have some what I will often refer to as a transition function, but it is something that is a basic building block is how to compute the next state, the resulting state of the execution of an action in a given state. And there are a lot of like so from the beginning to the end. So situation calculus is probably the first one, and we have all these like nowadays like I think that extension of formalizing action and change have been recently introduced. For example, there are different research that it involved like getting temporal logic to action theory or something like that. And similarly, like in the development in planning that corresponding to the, but I will talk like, I will jump from the beginning to the end in this talk. Now let me first give you a glimpse of like the solution to the three problems. Like the one of the particular action, formalizing action is the action language B, not B star. The star is for the reference here, right? So syntactically, it is a very simple language that if we wanted to describe an action that, let's say we wanted to describe the action move from C, move the block C from the block A to block B, we would write like say the first statement say that move C from A to B causes block C to be on the block B, right? And then when this action can be executed, it is executed only when C is on A and B is clear and C is clear. And then we will also have like something, what does it mean to be clear, right? And so C is clear if there is no block that is on C, that is dependent C, right? So that is, so this is a kind of like this language allows us to represent this, what the state constraint in this kind of form, and there is no constraint on that. And the semantic of this language is kind of like can be packed into just a single equation. So it says that it is basically when you execute an action in a state, which is an interpretation of all the fluents, then you might result into multiple states, right? So this is a function from the set of action and the set of possible state into the set of possible states. And it is said that S prime is a possible successor state if it is the solution of this equation, right? And this equation have three parts. The first part is like the S prime intersect with S is what basically what was true before is still true now, and then the direct effect of the action like that. How I will skip the details here, but like and then this Cn is the consequent operator applied on the static causal law, viewing as a rule, right? One important thing to note is that this computing this S prime could be computational hard. It is like NP complete, and you can see that in the next thing. So now, why do we want to work with static causal law? It's one of the things that this static causal law help us to resolve the problem of the ramification problem. That is one of the hardest problems in reasoning about action and change. And so I can illustrate the problem. I wanted to illustrate the problem with a very simple example. Now, I call that the domino problem. So here we have like n dominoes that are standing up from left to right like this. And then here we have a ball that if we swing the ball, then the first one will fall down, and then it will trigger all the others to fall down. If we have an action, if we have a plan like this, if we have a planning problem like this, everything is standing up at the beginning, nothing happening, and so we wanted to have the last domino to be down. Then what do? That's the action. So the solution is simple. There's only one. We just need to swing the ball, right? And so. One thing that when I start working in planning, I noticed that there's not many planning systems that deal with this static causal law directly, right? So most of the time, it is done either ad hoc or mm, uh, or it is said that we can translate the domain with static causal law into a domain without it by adding action and fluent. But then the size, the length of the plan is going to be big. If we have n domain, dominoes, we require a planning of the length n, right? So that's the kind of thing. That is not great. And if we, so, um, and that is one of the reasons I believe that we need to build system that are capable of dealing with static causal law directly. And the other thing is that sometimes this is an example where we cannot translate it, a domain with static causal law into the in domain without it, right? So it is because of in here, so this is the first two are the state the constraint where it is cyclic, it unstratified features, and it become so in this domain, even the action is deterministic, but its behavior it becomes non-deterministic. So you execute this action here, it becomes like two. You have to have two of that. So that is one of the things that is going to important. Now, fast forward. So here is basically a very quick comparison between the planning domain representation and the action language B. Like we have like the only difference, as you can see, it's only this unstratified, unstratified static causal law that is a problem. But it's already in 2003, Silver already showed, and co-authors already showed that if you are able to deal with the axiom directly, then the performance of the system is getting better. But the difficulty, I see that sometimes if you have to deal with this static causal law, thing is going to be more complex, right? So with that, I wanted to mention also that since then, since 98 until now, there are a lot of formalism of action and change, and also in planning that extend the representation language to allow different features of practical domains, quote unquote, right? So, for example, sensing action that allow us to deal with like belief of the agents when the agent doesn't have complete information, what's going to happen, right? And like or non-deterministic action or probabilistic action and numeric fluent. I'm sorry. It's also a problem. And then also action with duration and continuous effect and so on and so forth. For each of these, we have an action theory, or we have a different formalism that deal with these features. And like PDDL 3.1 have a lot of these features in there. What is new in each of these settings is that whenever you have a new, landed in a new setting, you need to basically define really precisely what do you mean by a state in that situation. It's no longer an interpretation of the fluent that we have. And for example, when you have incomplete information, you need to go with the belief state, right? And then when you have the notion of the new state, you have to develop algorithm to deal with like the transition from one. Right? So I will now move on from single agent to multiple agent and illustrate the issue that we need to deal with when we jump from one setting to another setting, right? And this is a problem that we wanted to formalize. So this is a paper that I work with Chita and other and my colleagues on that. And so assuming that we have these three agents, A, B, and C, which inside a room there is a box that is closed, but inside the box there is a coin that nobody knows that it's the coin line head or tails up, and in order to open the box, you need to have a key, and only A has that. And if you pick pick into the box, and while other is looking at that, then the other person would know that you know the value, the status of the coin, but doesn't know, but that person doesn't know it, right? And all this, so this thing. Now, given this domain, of course, all of these are assuming, let's say, that it's a common knowledge among all of them, right? And we ask the question whether whether A who has a key can learn the status of the coin, and let B know that he knows it, but doesn't let C know that he knows it, right? So, and for us, it's very simple. We can devise such a given the kind of like the description, we can come up with like this plan, right? First, let distract the C guy, and then signal the B guy to look at B, and then open the key, open it, and look into that, picking into the box. Now, to the best of my knowledge, there's not many planning systems that work with in multi-agent domain, right? In epistemic reasoning, can generate this plan still. What are the difficulty in dealing with this kind of thing? Now, there are now, given that the domain that we have, or the intention that we wanted to do, what kind of state do we need, right? We need to look at, okay, we wanted to represent and reason about belief of agents. So maybe we could use key structure that have been developed for this, precisely these purposes, right? Now, let's say, for example, here is an example of a key structure that representing the fact that nobody knows the status of the coin. And it is common knowledge among them that nobody knows that, right? So, and the second thing, so maybe we have the answer for our purpose, what is a state. But then what is the difficulty in representing about the action effect? Is the effect of an action now not only could be on the environment also, but could also be on the belief of other agents, and depend on whether the agent is aware of the action occurrence. If I turn on the light and you don't know that, then you would not be able to reason that the light is on, right? And then also, like, agent belief and knowledge could be depending on the action occurrence in different way, could be manipulated, right? So the other thing is that we also need to develop algorithm for computing the initial key model. If we were to use that, if we were to use key model to represent that, right? I believe it is not quite reasonable to say to keep a program a key structure and say that this is the key structure that satisfies all the formula that you have, because it is very different than in propositional logic, where we have a set of fluent and we can generate all the possible state and satisfy, looking for a state that's satisfying the given formulas. It is because there may be infinitely many key structures that satisfy a set of formula, right? So this is something that also something important to note. But I will not go into dwell on that. I will just now, from now on, I'm going the easy way, just assume that there is an initial state, initial key structure that's given to us, right? Now, how do we represent this domain? As turned out, syntactically, we can do it very simple. We still have the word altering action, the action that change the word, right? And we can use the statement of the form in the same way as in action language B. But we also have, and similarly, sensing action is the same. We can represent that in a paired way. The announcement action could also be represented in a similar fashion, right? So those are the actions that are happening in a multi-agent domain. So specifying the effect of the action is not a difficult part. What is that missing is that we will also need to, because we are saying that the effect of the action depend on the observability of the agent occurrence about. So we need to represent that kind of thing. And we divide, for simplicity, I think in this first paper, we divide this, the set of agents into 3 groups. One group is we call that full observers who basically know that the action occurs and it's aware of the effect of the action, and hence know exactly what is going to be the next successor state of the environment, right? And then the partially observer people who basically know that the action occurs, but doesn't know what the effect of the action. For example, I pick into the box and you observe, so you know that the action occur, and you know that I know that, but you do not know exactly what is the outcome. Right? And then those who are oblivious, who do not even aware of the action occur. Right? So we propose to specify this using a statement like this, right? Who observe what, who partially observe what, under what condition. So this is simple. And now, the most difficult part is what is then given a KPI structure representing the current state of the world and the state of the belief of the agent. What is going to be an action occurs? What is going to be the next one, right? So the semantic of the action basically rely on the notion of event models that were developed by the DEL, the dynamic epistemic logic people to investigate like action in multi-agent system. So given a, let me just bring them all up. Given a KPI structure, we can determine based on the specification who is the observer, who is the fully observer. Like this group of people, the full observer of the action of current, the partial observer, and then the oblivious, right? And then if the action precondition or the action executability condition is psi, then we can automatically construct the, depending on the type of the action, we can automatically construct the event model for each action occurrence. So in essence, we provide an answer that basically a very long-standing answer in dynamic epistemic logic is that where does this event model coming from? So if you read dynamic DEL paper, it's always, okay, I have this action occurrence, this is event model corresponding to it. It's very difficult to understand where does this come from. It is an art, right? So at least we provide a way to automatically construct this event model. Right? And now, after we have this event model, it becomes easy because it's just a cross product of this event model and the key structure. Now, here's an example. So here I'm just, let's assume that A is already opened the door and B is looking and C is not looking, for example. And this is the bottom left of this one, representing the event model of A picking into the box, while B is looking and C is not looking, right? So you can see that on the very difficult. Can you see the pointer here? It's like the bottom 2 event basically represent the event that B thinks could be true, like either the head is true, the head is up, or the tail is up. But for A, he knows precisely what it is, right? And C is still in the dark, she doesn't know anything, right? So, and then the gross product of these two would give us the result, the outcome, that is the expected outcome in this case for us, right? Now, this formalism facilitates the development of a planning system that capable of generate the plan that we have discussed. So I have mentioned earlier, right? And so now I wanted to quickly mention a little bit about the related work. There are a lot of work on formalizing actions or investigation of action effect in dynamics epistemic logic. What I can see is that the work, so in this line of work, the main thing is like the development of logic that allow us to reason about the effect of an action. And the thing is that in most of the cases, the update model or the event model is basically given, and you have to give it if you know that. And basically, the development of this event model has never been precisely described how it should be constructed. And or other formalism, other action languages, like, for example, the DEL action language that is very similar to MA star, developed by Michael and Rajan Natham. So they consider the language is different, but also they keep a way to construct the event model on the fly in the same way. But there are in planning, in multi-agent planning, there are a lot of investigation on how to approximate the reasoning with a bounded depth. Like, say, for example, I only consider the belief formula up to certain depth, so doesn't deal with like common knowledge, for example. And this have been result in many good implementation have been described by many groups, like for example, Yongmei Liu groups or Mui's paper in different ICAPS and in AIJ as well. Now I wanted to describe a few issues or partial open issues that I feel like it's important to address in this research. And the first one is that I believe that belief revision is needed here. Why? Because of agent can become ignorant or agent can easily have false belief after certain action occurs. And it is like in most of the formalism, if the agent have the false belief, and then you have the action occurrence generate using like the event model like that, you would have the action like the result is very counterintuitive, right? And the other thing is to deal with untruthful announcements. Most of the time, like there are only a few papers that I found that deal with, like, let's say untruthful, like I'm telling you a lie, right? But then that doesn't consider, like, it will always assume that I'm telling a lie to everybody. The updating is very different if, say, for example, if I tell a lie only to you, and then the other people, I don't say anything, for example, or the other people is even not aware of what I'm doing. So it's kind of difficult and then the other thing is that I have not seen this kind of thing, this kind of research, this investigation before. Say, how do people accept the announcement, right? It may depend on the attitude of the person. If I'm kind of like eager to change my belief, everything new, and that is what have been done by belief revision, right? Everything new coming in will override the old one, but now it's a belief, it's arbitrary. It depends on my attitude to accommodate that, right? So it's very difficult to do that. And the third one is like the inertia of higher order belief. And this is also very interesting. So we have a lot of work, I believe, that have been done in like about second order false belief problems, but higher than that, I have not come across to that. Right? What would be the common knowledge of everybody? After certain action occur under like arbitrary conditions, that is very difficult. Now, with that, I will leave the research in reasoning about action and change and planning in multi-agent domain. I leave you with some questions here, and if you have some solution, I would be happy to hear that, right? And so I wanted to a little bit focus, moving on to the new AI area where I don't know how about you, but I often have to correct people. Oh, you're working in AI, but not the AI that you know, that you think about, right? So this is very difficult, and then what is important in the explainable AI? Because of the development of the other AI, now all of our systems have to be able to explain what we are doing, right? And AI system or planning system or reasoning about action change, we need to do that as well. And let us just look at this very casual conversation between the operators and the mass rover, right? And the operator would just say that, hey, rover, go to the crater, the battle crater, and check out X, Y, Z. But then the rover say that, oh, I cannot do that. Why you cannot do that? Because my battery is down, right? If I go there, I just be dead there, for example. I cannot come back. And this is a very, very simple problem, but involving multiple agents, and one need to basically explain why one cannot or can or cannot do something. And in this situation, the explanation is very simple. It is a piece of missing.
Attention all, a test of the fire evacuation system is about to commence. This is just a routine test. Please do not evacuate the building. I repeat, a test of the fire evacuation system is about to commence. This is just a routine test. Please do not evacuate the building. This is a test and a test only.
Okay, so this is a test only, right? And I think that
emergency. Evacuate now. Evacuate as directed. Evacuate as directed.
okay.
Attention all, testing of the fire evacuation system is now complete. I repeat, testing of the fire evacuation system is now complete. Thank you.
Okay, we don't do that because we hear that we shouldn't do that, right? That's the explanation. So, and the research in the model reconciliation problem, it basically it's created out from the planning community mostly, and it very like one of the things we can use to provide explanation for AI system that deal with planning problem, right? Here you have like the two parties, the rover and the robot and the human. Each of them have their own quote-unquote planning problem or action theory or whatever you call it. But the two of them differ in or disagree on some issue. Here, let's say, for example, going to this crater, like the plan by stars. does and the other doesn't allow for that. So so the explanation is defined by, so there's some piece of information that may be missing from the human, and then some piece of information maybe redundant or is not true, and then the solution is a pair of information that should be deleted and should be added to the knowledge base or to the problem of the other party so that it works, right? And there are different classifications, different dimensions that model reconciliation problem could be tackled, right? For example, it's the complexity of the planning problem that that is considered by the agent. If we have a classical planning, it will be different than if we have a planning problem with incomplete information, right? Or if what is the knowledge of the explainer? In this case, for example, what is the knowledge of the robot about the model of the agent, right? So that is like, if I know exactly what is your model, I will be easily to be able to figure out what is an explanation. But if I do not know that, what's going to happen? And then the next thing is like, how much is the communication allowed? We have only one shot, or we have multiple shot, like the explanation can expand like that. And then it's also possible to consider, that need to be considered, that whether the agents are trustful or not. Or maybe if they are trustful, but the way they generate the answer may be incorrect. So what is going to happen, right? So this is the kind of thing. So this is probably a generalizing model for model reconciliation for explainable AI, that I think that it could be something that for a long research here, like, so we have two agents with different knowledge base. The knowledge base may be a planning, the encoding of the planning problem. And then, I propose that we should, and then we assume that I do not know, or the agent do not know about the other agent. It may have some belief about that. And so we will need to start the conversation with a pair of mind. So this agent knowledge base, and the belief of it about other agent knowledge base. And so the conversation to resolve a disagreement should be on like iteratively, similar to the negotiation, but it's different because we assume that, let's just say that we assume that they collaborate with each other to do so, to resolve the disagreement, right? And so the need here is that not just only representation, but also the algorithmic. How do we calculate the explanation for each of the steps, and how do we update it, each of the component of this knowledge base, right? And this is something I believe that. Oh, now I think. So the knowledge base here, we could imagine that it's just basically the word model of the agent, right? And so the more complex this knowledge base, the more complex the word model, the more complex that is going to be the process. And now let us say that if we were to have agentic AI replaced by this agent, what is that we can expect? We could expect that the communication language could be, we could use English or whatever language that is, right? And then the disagreement will need to be resolved through exchange, through dialogue, similar to in model reconciliation. Now, my hypothesis is that in order for this to work, the agent must have a very correct representation of the world model. Right? So now, if LLM can do the job of creating the world model for the agents and being able to reason and plan, perhaps we don't need to do research anymore, right? And so now, but I wanted to give you an example to show that we still have a lot to do. And this is what I did. I give this ant story to LLM. You can see that the story is very simple. It's describing an ant that goes left and right, but with some constraint. Like here, it goes at any moment of time, it can go left or right, one step at a time. And whenever it moves to the left, 2 consecutive steps, it moves back to the right 1 step. It's very simple, right? And I asked the 2 Gemini and ChatGPT the question: how many steps needs the ant make in order for it to position it to the left 5 steps? How many do you think it would be? It needs? So it answered me very quick. And Gemini say 11, which is correct, right? Because it moved to the left twice, but then have to move back. So 3 steps for 1. And then repeat it 3 cycles. It takes 9, and it is a 3. So it moved two more, so it's 11. Very correct, very nice. ChatGPT simply say it's 15. No matter how much I try to tell it, like, maybe you need to rethink it, right? But it doesn't. It's very firm on answer. The interesting part is the following. How many steps it needs to do in order to go 5 steps to the right? What is that? Would be your answer? 5, right? Because I'm just giving to go to the 5. Both of them answer it is impossible. And I was so surprised. I said, why do you think it is impossible? And then I decide, can you give me the PDDL representation of the domain? And then the 2 of them, give me a very precise PDDL domain with 1 single exception. Both of them added to the representation 1 more constraint that say, whenever you move to the right 1 step, you have to move to the left twice. I was so surprised. I said, why do you think that it's so? And it said that, and I even asked, is there anywhere in the text that say that? No, there's nothing in the text say that, but I decide that it needs to be added so that the theory is symmetric. And I added that for the simplicity of the representation. So I believe that I was thinking that one more thing is that I wanted to point out that Jan LeCun in his broadcast said, we won't be able to reach AGI if we are scaling up LLM. What does it mean is that doesn't matter how LLM is going to be improved. The agentic AI, if we believe Jan LeCun, would not be able to reach the human level AI, right? So I will leave you with the final thought on, like, okay, so if it is the case, how do we reach the human level AI program? Perhaps by asking LLM to help us analyzing the text, because analyzing the text is not an easy task. Come up with the word model, and then let the reasoning and planning to us, right? So I conclude here with thanks to my collaborators and the funding agencies that have sponsored me for throughout the years. Thank you very much.
Thank you very much. We have about 5 minutes for questions, minus the fire alarm. Any questions?
So, hi. Is there any hope that LLM can create a proper theory? I mean, without making the mistakes you mentioned to make it nicer or whatever?
That's what I hope. And that's why I think that we can work together with to remove that thing. But I do think that I don't need to repeat. A lot of planning research already show that LM is better at planning, right? And a lot of other research saying that it's bad at reasoning. It doesn't matter whether tree of thought or train of thought or something like that. But I do think that what we can do, it's first of all, why do we remove all the tools, the wonderful tools that we have developed for certain purposes, right? So what it is more difficult is like to teach a student how to go from a very simple text to a problem representation that the machine understands. And currently, what we do is that we keep the text and then we ask it to solve the problem, which I think it may not be the right way, because I believe that the ant story that I come up with probably have not been seen by the LLM. So that's why it's a weird thing happening. And if we ask LLM to solve for us the problem, basically we won't get what it repeated, what it has seen before and repeated now. And I recently talked with Chitta, and he has a paper where he mentioned the term phantom recall, where he take all the puzzle that we all know, like the and then he just remove one thing or added something to that to make the problem much easier. Say, for example, I think the garbage and the wolf and the example, right? Where you have the boat and then you have to schedule this thing to be very precise. He said there are two boats, right? There are two boats, and then you still get exactly the solution that was it. So if we do that, then I don't think that we have any hope. But I think that LLM could be used to kind of like, if you keep a text and ask it, okay, what are the actions? What is the effect of the action? It would do a much better job than that, than try to solve the problem with it. So I think that there are hope.
Hi, Son. Thank you very much for such a wonderful talk and for sharing so much of your great work with us. It was really an enjoyable talk. One of the things I was curious about your opinion about, so you talked about your work on M** A and on using a Kripke structure. And of course, in logic, we know that we can either reason with formulae or we can reason with the models. And often we reason in formulae because they are compact and finite and elaboration tolerant and have all sorts of nice properties associated with them. I'm wondering whether in the context of epistemic planning and some of the work that you've talking about, whether you can talk about the pros and cons of reasoning with models, like Kripke, like possible world semantics, versus reasoning with respect to formulae, which is something that I think the ICAPS community in particular is more familiar with, because I think there are pros and cons to each, and I was wondering if you could just elaborate on that a little bit. Thanks.
Thank you for the question. I think my view of that is that it depends on what you need. Whether you, say for example, if you wanted to deal with common knowledge, for example, I don't know how it is, whether it is easier or it is more complex to deal directly with the formula, like how to change the common knowledge to something like that. I think that need to be done in order for planning with. If we just limited the depth of the belief formula, then I think that perhaps reasoning with depth-bound formula and directly with the formula is better. But if you wanted to deal with common knowledge, then the compact representation of the Kripke model may be better. That's my opinion as of now. Yeah.
Thanks.
Okay, last question, Nello.
Thank you for this wonderful talk. I have a question about the issue about belief revision. It reminds me something about in the knowledge framework, I mean, the update of observability. This is called in several ways. Is this correlate? Because we have done works in that side about changing of observability. It also reminds me the work of synthesis by Rosner, where there is a visibility of knowledge and is changing. So there has been some work, and I was wondering if they are correlated. Of course, in our field of knowledge representation and reasoning with the knowledge, with the epistemic logics in strategic reasoning, everything becomes undecidable when you mix this visibility. But yeah, I would like to hear if these two words are connected somehow.
I must say that I wonder whether you refer to the paper synthesis of Bartak or what. Or do I not understand your question?
Yeah, the synthesis paper is about Rosner. I mean, the one that started with this model checking of open systems, so synthesis of open systems, so modules. And of course, I mean, there is in that case it's two player, and they also did in multiple player setting. And in that sense, I mean, it's imperfect information. It's not even knowledge, but it's imperfect information. There is a visibility. Actually, they prove that when there is a hierarchy of visibility, everything is decidable. But when you mix the visibility, it's undecidable. It's what at the end, I mean, makes ATL, for people that know ATL K with the imperfect information and you know, with the memory full, it makes everything indecidable. But then, I mean, there are some works on changing of observability. You can see and you change your mind. So, I mean, it's also related to other works like, that's, I don't want to open to other direction, but that's what we study in the
I must admit that I'm not aware of the work, so it may not be. I may not be able to provide a right answer for that question. But I was when I refer to belief revision is needed here, I was kind of thinking of like whether there is any set of postulates that we should develop for similar to the HEM postulate for belief revision in single agent situation. And that is the thing that I wanted to think about. Unfortunately, I'm not aware of what you refer to, so I cannot say much in that direction.
Okay, we can talk.
Maybe we can talk about that later. Yeah.
Thank you.
Okay, I know there are probably some more questions, but we are now at a coffee break. And thank you very much again for wonderful talk.
Thank you very much. Yeah.